Okay, let's dive into this fascinating journey of how our digital world actually connects. Welcome to this explainer. Today, we are completely decoding the invisible roads of the internet. I mean, we interact with computer networks literally every single day, but rarely do we actually stop and think about the incredible hidden architecture that makes it all possible. So here's a kind of mind-bending question to kick things off. How does a server all the way in the USA feel like it's sitting right inside your laptop in India? When you click a video on Facebook or search for something on Google, it opens in a matter of seconds. It's an absolute engineering marvel when you realize that data is crossing literal oceans, yet it feels completely local to your device. How on earth do we achieve that kind of insane speed and abstraction? To really get how this works, we've got to get on the same page and establish a baseline. What exactly is a computer network? Well, fundamentally, it's a collection of various computing devices connected through wired or wireless means with a primary purpose of sharing data. Whether those devices are exactly the same, like two MacBooks, or completely different, like your smartphone talking to some massive server farm, and whether it uses a physical wire or an invisible wireless signal, the entire goal is simply moving information from a sender machine to a receiver machine. So here is the roadmap we'll take today to unpack this invisible infrastructure. We're going to start with the magic of connection, figure out how these machines speak the exact same language, look at the mandatory versus optional rules they follow, break down the famous 7-layer OSI model, and finally we'll scale things way up, going from tiny personal networks to massive wide area ones. Section 1. The magic of connection, beyond the operating system. So, the crucial point here is that we need to zoom out from the hardware sitting right in front of you. Think about when you press a key on your keyboard and that letter pops up on your monitor. That is what we call inter-process communication. Both the sender, your keyboard, and the receiver, your monitor, are part of the exact same machine. Your operating system handles all of this flawlessly. But true network communication, that's an entirely different beast. It only happens when a client machine requests data from a physically separated server machine. The client and the server are completely distinct physical entities. And that brings us to this incredibly cool concept, the abstraction illusion. Because really, the ultimate goal of a computer network is to provide an environment where these two completely physically separated machines feel like they are literally the exact same machine. It makes a Facebook server 10,000 kilometers away in the US load data on your screen as fast as a movie playing directly from your local hard drive. The network completely hides the distance. Whether it's 1 meter or 10,000 kilometers, it creates this ultimate illusion of closeness. But you've got to wonder, how do we maintain this illusion without everything just breaking down into total chaos? Moving right along to Section 2, speaking the same language, the need for protocols. Let's look at a human example for a second. Imagine a phone call where the sender speaks Punjabi, but the receiver only understands Telugu. I mean, sure, a physical connection absolutely exists. They can hear each other's voices just fine, but there is literally zero communication happening because the receiver cannot comprehend the data. However, if both people use a standard protocol, like a shared language, boom, you achieve perfect communication and data sharing. In computer networks, simply plugging in a wire isn't enough. The receiving machine must actually understand the incoming message. That shared language in the digital world is what we call a protocol. A protocol is simply a shared set of instructions running on both the sender's and receiver's machines to ensure the transmitted data is perfectly understood. It's the agreed-upon rulebook that guarantees proper communication across the connection. So now that we know what a protocol is, let's look at the strict rules they actually enforce. Section 3, mandatory versus optional rules. Filtering the chaos. Get this, 70. That's a huge number, right? When your laptop talks to a server, there are over 70 different network functionalities working simultaneously to ensure your data arrives safely. It is a massive, highly coordinated operation running in the background every single time you click a link. And this brilliantly illustrates how we actually manage all that cognitive overload and system complexity. We take those 70-plus functionalities and divide them into two main categories. Mandatory functions like error control, flow control, and multiplexing, and optional functions like encryption and checkpoints. We have to separate these because if we didn't, we'd slow down every single network request with incredibly heavy, unnecessary rules. Let's dive into those non-negotiable mandatory functions first. Honestly, the whole network completely breaks down without these. First up, error control.
The internet is an open system, right? It's full of noise and interference. This function ensures that if you send message M, it doesn't arrive totally corrupted as M1. Second is flow control. Think of this as a traffic cop. It prevents a super fast sender from completely overwhelming the receiver's limited buffer memory, which would just cause massive network congestion. Finally, multiplexing and demultiplexing. Since you probably have a dozen programs running on your machine right now, this ensures incoming data is routed to the exact correct process, sending an email straight to your inbox and a video directly to your web browser.
But things get super interesting when we look at the optional protocol functions. Take cryptography or encryption. If you're using an HTTPS banking app to transfer your money, encryption is absolutely vital so hackers can't intercept it. But applying that heavy cryptography to literally everything, that increases system complexity and processing time way too much. The exact same goes for checkpoints. If a huge 500 megabyte download fails at 301 megabytes, a checkpoint lets you smoothly resume at 300 instead of restarting from 0. But we skip those checkpoints entirely for tiny, simple data bytes, like a quick WhatsApp message. Adding that heavy functionality there would just bog down a fast, simple system. So with over 70 mandatory and optional rules floating around, how on earth do we keep them organized? Which brings us to Section 4, the 7-layer OSI model, structuring the rules. To keep all this organized, computer networks rely on this ultimate standardized playbook called the Open Systems Interconnect, or the OSI stack. It organizes all those functionalities into 7 distinct layers. Think of it kind of like an intricate postal system. The application layer writes the letter, the transport layer packages it up, and the physical layer actually drives the truck. Every single network function we just talked about lives inside one of these specific layers. Now, what's really fascinating here is that this layered gauntlet, it is completely non-negotiable. Every single message you send has to pass sequentially down through all 7 layers to securely leave your machine. And when it finally arrives at its destination, it has to reverse the whole process, traveling back up through all 7 layers to actually enter the receiver's machine. By following this incredibly strict protocol stack, we ensure data is perfectly prepared, sent, and received every single time. All right, we've explored the invisible software rules, so now let's shift gears to the physical roads our data travels on. Section 5, Scaling Networks, PAN to WAN. Take a look at how this scales. Physical distance actually dictates the entire nature of a network. It scales all the way from a PAN, or personal area network, covering just a few feet, right up through local and metropolitan networks for campuses and entire cities. And finally, we reach the WAN, the wide area network. This is global, it's public, it is incredibly expensive and extremely difficult to maintain because you are literally connecting entire countries. The rule of thumb here is simple: distance directly correlates with hardware complexity. Just to really highlight that extreme technical contrast, think about a PAN. It's basically just a 10-meter Bluetooth connection beaming a photo across your bedroom. It uses built-in hardware, requires basically zero maintenance. It's super easy. Compare that to a WAN, the World Wide Web itself. It's utilizing massive leased fiber optic lines sprawling across literal ocean floors, alongside incredibly complex routing hardware, all just to successfully connect data across international borders. But here's the fun fact. Where do you think the architectural blueprint for this massive internet actually came from? It was directly inherited from old-school telephony. Pre-1990s, telephone networks relied on PCO for local calls, STD for interstate calls, and ISD for international dialing. When the concept of the modern internet arrived in the 1990s, it adopted this exact same structured framework. So today, your local LAN acts just like a PCO, your citywide MAN is like the STD, and the global WAN serves as the international ISD. It is just an incredible evolution of a much older framework successfully scaled up to billions of digital users. And that brings us full circle to this brilliant quote that perfectly summarizes our explainer today. The functionality of a computer network is that the client and server should feel that they are present in the same machine, but actually they are not. Whether your data is passing through the 7 strict layers of the OSI model or traveling across a massively expensive wide area network, the ultimate goal of all this complexity is that amazing abstraction illusion. We just want a totally frictionless experience for the user. So I want to leave you with this provocative thought, kind of a quick test of what we've covered today. Based on your current range, your specific hardware, and your internet connection, are you actively using a LAN, a MAN, or a WAN to stream this explainer right now? Take a quick look around your environment and really think about the invisible network rules operating right under your nose.
Keep learning, keep questioning, and I'll see you in the next explainer.